I would like to thank you for the possibility of talking. I feel very honored to be talking to this audience. It's somewhat like talking at your home institution, which is always a very important thing. I'm going to go over a lot of different subjects.
Oops, you're also taller than I am, so we need to be properly having your mic.
Okay, is that better? I'll be talking about a wide range of applications, and I hope I can leave you with the sense by the time I get to the end that all of these different applications and techniques hang together in a certain manner of speaking. So we'll be going from meters to micrometers and below, and looking at different hierarchical structures within mineralized tissues. And these are typically strategies that have evolved over time to optimize or at least greatly improve the properties of the tissues. So I wanted to cover a little bit about these hierarchical structures, overview the techniques and the size scales that I will talk about. That's not everything I've been doing with mineralized tissues, but it's the stuff that I could fit in. So we went through some specific examples, one of a Roman era Egyptian mummy, and then some archaeological metacarpal bones from various cemeteries in Europe. Talk about then in a smaller size scale, beluga whale teeth and beaver teeth and what we can learn about growth patterns there. 3D printed scaffolds for spine fusion. Hopefully you will not have to deal with that kind of operation, but increasingly patients are needing to have their spines fused for stability purposes. And then finally talk about a stochastic sampling process, or where we're looking at the rod structure in human tooth enamel. And then I'll have some concluding thoughts. I'm not quite sure what those will be right now, but there will be some at the end. In bone, we have a bunch of hierarchy of structures. So we have solid cortical bone and trabecular bone, fenestrated type of structure here. There are canal networks. There are differences in mineral level within the cortical bone. And we can go all the way down to the nanometer level where we have collagen fibrils that nucleate mineral, hydroxyapatite. Sometimes I'll call it carbonated apatite. And the collagen triple helices will have an intimate relationship with the mineral particles. And we characterize these in scattering terms by D period and D spacing. This is a micro-CT picture from 2BM where we're seeing different mineral levels. In tooth, which will be another one of the principal examples, we have enamel on the wear surface, dentin in the interior, and cementum where the periodontal ligaments attach. We're going to look at, in my talk today, the hierarchical levels of band structures within the dentin and cementum. And we notice that there's a slightly different arrangement of collagen relative to structures like the tubules extending through the dentin. And once again, a very intimate relationship between the mineral and the collagen fibers. So I'll be talking about various X-ray techniques, imaging, scattering, fluorescence, and size scales of wanting to see things with sort of millimeter resolution over samples that are meters in size, 0.1 millimeter over centimeter size samples, microns over millimeter distances, and submicron over submillimeter size samples. And we fill this in by position resolved scattering fluorescence imaging, the larger scale an Egyptian mummy, slightly smaller scale the archaeological human metacarpal bones, then beluga whale teeth are slightly smaller, 3D scaffolds for spine fusion, the beaver tooth, and then human enamel as we get down to submicron levels. Throughout all of these applications, we're learning something about structures and its variation that affect the performance and or development of this. The common themes are in the mummy, First of all, I was just looking to see if we could see mineralized tissue and identify other constituents. And basically, this applies to an in situ, in vivo examination of actual living people, perhaps. Archaeological metacarpal bones. I was interested in whether the lattice parameter, which is a fundamental characteristic of the mineral phase, whether that differs for an active population versus a sedentary, say, modern population. And we wanted to look at osteoporotic versus competent bone. The tooth growth bands, that's the beluga whale and the beaver teeth, relationship of development processes to the physical properties that result from the tooth, 3D scaffolds for treating disease, i.e. the spine fusion operation, basically getting new generation of material and figuring out how they work to promote bone healing. Human enamels, nanostructure is an important record of how the mineralization occurs, but also its nanostructure affects wear and chemical resistance. Very important to know. So the first example is the Egyptian mummy. This was maybe the most unusual experiment I'll ever be involved with for a variety of reasons. We're doing in situ position resolved X-ray diffraction. These are the people involved in the study directly, and these are our acknowledgments to various people. We're combining and guiding the experiment with computed tomography so that we can put the X-ray beam exactly where it needs to be to find a particular structure. This was sort of challenging. This came about because there was an exhibit planned beginning in 2016 for characterization of mummy portraits from Roman Egypt. For a certain period of time in Egypt, when they mummified someone, they would wrap them up and then they would stick a portrait of what the person was supposed to have looked like on the front of that. And this is the portrait there. So this exhibit was happening, and one of the curators happened to walk into the Garrett Theological Seminary Library, which is in the middle of Northwestern's Evanston campus, and walked by this, looked at the front of this, and saw the portrait, and realized that this was closely related to the materials that would be on exhibit. So we actually had a sample that we could study and do CT on. It's a very rare object. This is the portrait of Hawara portrait mummy number 4, and this is a rendering from the CT scan where you can see actually quite a bit of contrast, which was actually quite surprising. We're interested in this rare example of a Hellenic painting and its tradition for age of death matching the portrait age, biomaterial focus on linen wrappings, resin inside the skull, and a couple of other contents of the mummy. So here is a simple projection from the CT data of the tooth development. And tooth development for children is the best indicator of age. So we make this age of death to be 5 plus or minus 3/4 of a year, and that's based upon unerupted permanent teeth and the presence of primary teeth. We infer this is a female, it was a girl, from the absence of external genitalia. We know that typically in a well-preserved mummy we can see external genitalia, i.e. males from females. So we would infer that this was in fact a 5-year-old girl when she died. Resin is used in the preservation process, and some of it got into the skull. What we have is an endocast of the skull, which is actually extremely rare because this is a conformal shell. The resin was actually very curved, and as far as I've seen, it's never been observed before. It's cracked because of handling, not by me, but before I got it. And one of the things I was most nervous about in the whole experiment was I knew it wouldn't happen, but I didn't want to be the person immortalized as burning holes in a mummy with an X-ray beam. Because if that had happened, people would be mentioning my name in a very negative way for dozens of years. The things we're interested in are some wires that we see in CT that were in the linen layers, and an inclusion F, which was quite absorbing on the abdomen, and then learned something about the femora, whether we could see signal from the femurs. Now, we needed CT. It was absolutely essential because we had only 1 day of beam time. If we were to just put a rectangle around the sample and study it with all the different positions, point by point, without any regard to any prior information, it would have taken us 19 days to cover the mummy. If we scanned everywhere where there's diffracted intensity, so we had a SMART program, it would take 11 days. So clearly we couldn't do this. We had less than a day to get in and out and do the experiment. So we used CT to know where to look. Now, there's one complication of doing diffraction from a mummy, and that is if you have one detector position, an area detector, and you have a beam coming from here, you cannot differentiate its position from position A, which could strike the same detector but at a different diffraction angle. So what we had to do was collect data at 2 detector positions, and then that allows us to trace back to the point of interest. So the first thing we have to do in the analysis was to trace back to this position, work out what the 2 theta was, work out what D was, and then relate that to what material was giving us our signal. So the mummy arrived at 6 a.m., unpacked the mummy, and there was all sorts of press and stuff going on until about 1. Collected data until 6 a.m. and then packed up by 8 a.m. for the next user. And I had to babysit the 5-year-old the whole time. You know, you can't leave a 5-year-old by themselves. They can get into a lot of trouble. So I was there the whole time, and things went very well. So here's a schematic of the diffraction. And there's 2 thetas. This is a typical diffraction pattern, and like is normally done at sector 1, we put it into Cartesian coordinates, and this allows us to see a little bit more clearly the crystallographic texture and to do other analyses. Here are the positions we scanned. We took a vertical scan through the sample, did all of our positions at the first detector distance, moved back to the second detector distance, and repeated the scan. So how well does the approach work? Remember, we're concentrating on the femur, inclusion F, and in this position here where we're looking for wires. So phase identification, can we identify what was there? Inclusions, wire, and bone. And can we see trabecular and cortical bone? So here are 2 patterns, and in order to do the ray tracing, this is at detector distance 1 and detector distance 2, we have to find the same feature in both. We take the radial position, and that allows us to get back to the Z position, how far along the beam that particular feature is. Once we know that, we can work out what 2 theta is, and hence the D spacing. So this just shows features that we traced back. Individual spots, which turn out to be dirt on the outside of the mummy, and these lines, from the texture, I can tell you that they're from bone, and a long bone in this particular position. So if we now first consider inclusion F, which is near the abdomen in this position, we see we have a bunch of continuous lines. In fact, these lines L are from calcite, and these are the first reflections from calcite. They index quite nicely. And the spots A through F, individual spots, are from quartz grains, which is a major constituent of soil, and they all trace back to the outside of the sample. This is the position where the L lines originate, and we find out that it exactly matches the position that we see in CT. So we identify this as calcite by its dimensions, which are something like CT says 7 by 3 by 5 millimeters, and the diffraction cross-section is sort of 7 by 5 millimeters. It's the right sort of size for the spiritual symbol or talisman, a charm that the Egyptians use, which is a scarab, the scarab beetle. And so we think that this was placed above the incision we think it's a scarab, first of all, and it's at the right position for covering the incision that's made in the body when they eviscerate the corpse. And this is very important because it therefore preserves the integrity of the individual so they can have a long afterlife. Wires within the linen wrappings, we see characteristic texture, and I won't go into any more detail other than this turns out to be a modern steel, and we think the wires were added during conservation in 2000. when the mummy was on exhibit in New York, but there are no records. So this is only an inference. The wire positions, once again, match. Here's a wire position, and here's a wire position. This is a section through tomography. And this very busy slide just shows us we're seeing the wires at the right place, both left to right and from up and down positions. So our identification is really good in terms of location, material. Now, my main interest is, can we get data from within a body, or within a mummy in this case, on bone? And here we see diffraction lines. This is the 002 hydroxyapatite line from bone. And we see texture that we would say would be characteristic of a long bone. So the bone axis is along this direction, so we have higher C-axis intensity here, azimuth there, detector radius. And what we can do is trace back these diffraction patterns. We can see the different lines splitting. And what is that from? That's from the front surface and the back surface of the femur. So these are the positions of the two walls of the femur. Remember, it's a round tube, and we have two of them. This is the uppermost one, and this is the lowermost one. And once again, we can see that offset, both in terms of the Z position and the vertical height. The D-spacings are consistent with what we expect. We found other things in the mummy that we didn't expect. We saw lines from calcite, and then when we went back to look at the CT, we looked right under this femur, and at this position, we see there's a large inclusion that is the same absorption as the calcite. So this is a large particle of calcite that came into the sample. We weren't able to see cervical vertebrae. We think the mass is too spread out. Our precision and depth location is 1 or 2 millimeters. We can resolve the femur's lateral and medial sides at about 2 or 3 millimeters separation. And what we could have done better was a little bit better data collection, because we have a high background of diffraction in the patterns. And this hinders extracting the normal information we would want to get out of analyses like peak broadening. So there are things to improve. I don't know that I'll ever get my hands on a different mummy to bring in, but if we were, we know better what to do. Second example is archaeological metacarpal bones. Once again, smaller, and we once again have the similar problem, namely the sample is fairly thick, thicker than we're used to, 15 millimeters. The samples are from 2 locations in England. We had 6 of each from Ancaster and Warren Percy, and 2 each from 3 different age cohorts at death. This is based on tooth wear, 18 to 29, etc. We have some reference samples. We use micro-CT to compare to the scattering results. SACS was also used because the collagen periodicity, the so-called D period, produces peaks in diffraction from bone, and this will indicate that collagen is present. If the collagen is all gone, the D period peak disappears, and you maybe get an idea that that sample no longer, for example, contains DNA. And moving forward, here's the second metacarpal bone. It's in the hand right here. It's a favorite of the anthropologists for reasons that I don't know exactly why, and none of them have been able to tell me, but it is something they routinely study. Photographs there. This is where we scanned with the microbeam, and we took measurements of micro-CT at this position, in this position, and then synchrotron micro-CT in this position. So what we see is within the Ancaster samples, we see variation in the cortical thickness. So I would say that these guys are older, and these are more young. There's a little bit more porosity here, so this would probably be middle-aged. And then we see similar behavior in the Warren Percy skeletons as you go across. So micro-CT gives us a picture that's reasonably comforting in terms of it matches what the age cohorts that we're supposed to get. Now, the problem we have when we want to do position-resolved scattering is our center of mass might be here, or in a different position might be here. A distance separation between the 0 position from which we were obtaining diffraction, differing by 5 millimeters, is not going to give us a precise lattice parameter. It's going to give us a problem. So we have to correct for that. And what we do to correct for that is we collect the data at 0 degrees, and then we match it with the same pattern at the same position collected at 180 degrees. And then what we do for each pattern is azimuthal integration, Rietveld refinement for precise A and C. Now, these precise A and C are not accurate because of this offset effect. When we go and average via this correction method of 0 and 180 degree data collection, we can now make it accurate. So this scale factor for the Rietveld just shows us that we in fact match the two. So 180 is in blue and 0 degrees is in green, and you can't see the blue, so we know we've got a perfect match in terms of the lining up of the patterns. If we were not correcting the data, at 0 degrees, our lattice parameter would vary as shown across the sample, each of one of these positions as we scan across, and at 180 it would look like that. When we correct by putting the centroid at the center of rotation, we end up with this graph. And that is just for an artificial sample. This is what we would see for one of the typical archaeological metacarpal bones. We see this sort of variation, and we once again get an effective correction. When we put all of those together, we see a pattern of lattice parameters going for decreasing trabecular bone volume fraction, which means age. We see the lattice parameters are all over. And this is actually not surprising because of the change of the bones, diagenesis, that occurs very non-uniformly, even at the same cemetery site. So what we're having is lattice parameter, it turns out, is not useful in this context. If we go to the intensity of the D peak of Sachs, which is telling us the extent to which collagen is present, we see one of the 6 Warren-Percy samples looks to have residual collagen. This is the modern reference bone. So we look like we have a lot of collagen remaining here, and 3 of the Ancaster samples also have large intensities comparable with the modern bone that's never been in the ground. So we think that 1 of 6 of the Warren-Percy and 3 of 6 of the Ancaster still contain collagen. And that is an important marker because if you wanted to extract DNA from these bones, those bones showing the collagen D period peaks would be the ones you would look at, the ones you would destroy. Now, I mentioned that diagenesis has changed the bones, that is, changes while they're in the ground. Here we see cracks within the bone in one sample. Here we see a crust of white material. By the way, none of these show any other phases other than hydroxyapatite. So this is recrystallized dense hydroxyapatite that's formed. We see microporosity in the stippled contrast, and then we see, this is the modern sample. Because this was done with white beam, we can't really see the remodeled osteons, but this reference shows us that, yes, indeed, the archaeological samples have undergone profound changes. So, not going to go through this slide, it's just summing up what I just said. I'd like to go on and move on to the development problem that we see within the teeth, beluga whale teeth and beaver teeth. And this is where we're combining scattering and position-resolved fluorescence. We're getting a map of what elemental constituents are there and how the diffraction signal, things like lattice parameter, change with position. So annular bands in tooth cementum. Cementum is the part of the tooth where the periodontal ligaments attach to the bone. So the bone is attached to the teeth. They are added continuously, the cementum layers are. These annular bands are seen in polished sections, and nobody really has established whether they're due to varying mineral content or crystallographic texture. They're very important in wildlife management and also in anthropology because this gives us a measure of age at death. Basically, one band is added per year. You get a light band and a dark band. So this is our method of measuring how old someone was or some animal was when they died. Obviously I didn't edit this correctly. Zinc is concentrated in your active mineralization sites where concentration of calcium was higher. So we know that zinc is related to active biomineralization. Since the beluga whale tooth is mostly cementum and has widely spaced bands, this was a good way to try to look at the chemical variation, i.e. the elemental information with fluorescence, and also to look at how that might correlate with X-ray diffraction in mapping. So here's a fluorescence map. This is the transmitted intensity collected at the same time that we had transmission through a thin section of beluga whale tooth. It's peg-like, so that's the outside there. This is the pulp cavity, very small in this. And we have maps of absorption, calcium, and zinc. And the color table in this zinc was not very good. So in a separate scan, we can see that we have upwards of 30 growth bands within this map of the same beluga whale tooth. So we know this animal was at least 30 years at death, and probably older than that. Probably more like 34, and then we'll see. So what we do is we get good match of the zinc with the absorption, and I'm going to skip ahead a little bit to this enlargement. So we see zinc matching with the calcium. The calcium is a strong signal over a strong background because there's a lot of calcium. Zinc is relatively low intensity there. It's the principal trace metal within teeth. And so we see all of these peaks numerically, and they also correspond exactly with positions of increased intensity. What we can do, because the data are collected on longitudinal sections that are thin, we can also do a typical diffraction mapping experiment and look at the integrated intensity versus D. That's this plot, and we see that enamel has very sharp peaks. That's be important later. And beaver dentin and beluga dentin follow this sort of curve of the diffraction pattern. Now, if we map the calcium and the zinc in this longitudinal section, the transmitted intensity, and the 002 and 130 diffraction peaks, we find out we have a good mapping. So when zinc goes up, diffracted intensity goes up. And absorbed intensity goes up. So the bands that we're seeing optically, as far as this tooth sample is concerned, those bands are due to increasing mineral content, which is also associated with zinc content. Now the question is, where is the zinc? Zinc is involved in many things like matrix metalloproteinases and a lot of other things that are implicated in biomineralization. Where is this zinc that's remaining there? So if we take a section, went to 2IDD with a small beam and did Rietveld refinement of the patterns and examined the correlation between the spatial variation of lattice parameter versus the zinc concentration. We can do this correlation exactly because the data were collected simultaneously. So there's the now defunct setup at 2IDD, the beam coming in normal, taking off the fluorescence detector and then measuring the diffracted intensity here. So this is a radiograph of this happened to be beaver incisor tooth. And so we could see in the radiograph on the line that there were differences of absorption. Not very interesting. It's nice to see, though, and suggested that we should collect data here. So here we have the variation of zinc fluorescence intensity in one of the scans. Below that, the variation of the A lattice parameter. And you see they're anti-correlated. When one goes down, the other goes up. If we do a scatter plot of the A versus fluorescence intensity, we see a more or less straight line. There's a lot of scatter around that, and that is very common in mineralized tissues to see that level of scatter. So in the incisor dentin, increasing zinc correlates with decreased carbonated apatite lattice parameter, the A lattice parameter. And this suggests that, in fact, the only way this could be happening is if zinc is incorporated in the hydroxyapatite lattice. This is sort of interesting because the hydroxyapatite, carbonated hydroxyapatite particles are very, very thin. So it might be we're far enough from equilibrium that we can get zinc into the lattice. Now, 3D scaffolds, to me this is one of the more interesting things I'm doing. I mean, mummy is very interesting, but this may actually have the possibility of helping real patients someday in the future. What we have in spine fusion is we want to immobilize adjacent vertebrae by fusing the transverse processes. Those are just things that stick out on either side of the spine, and this would cure, by immobilizing the sections, the pain and vertebral instability, that is sliding of adjacent vertebra. In 2013, this is how many spine fusion surgeons there were in the US, costing more than $42 billion. Expensive. Now, the real rub is that in 10 to 15% of the patients, the surgery doesn't work. And you got to go back in and do something else. This is unacceptably high. We need to improve the process. So we're trying to get a new scaffold. So it used to be that they would treat with bone morphogenic protein 2, but we found out there's a lot of side effects from that. So we're trying to get new scaffold materials and investigating this in a rat model. So fluorescence and diffraction mapping was done, and also some diffraction tomography, trying to learn how to study these scaffolds. The fusion process involves taking off the cortex of two transverse processes on the sides of the vertebra and then placing a scaffold over that, the scaffold being there to encourage bone to grow across the transverse process, thereby immobilizing those two vertebrae and removing the pain. So here is one of the scaffolds that we're developing, and there's the bone. These are the transverse processes, here and here. This is the beginning of the vertebral body. And this particular system that we're looking at is 3D printed. It's a hydroxyapatite, synthetic hydroxyapatite, with an elastomer scaffolds. Our goal is to use no BMP2. As the first trial, we used the synthetic hydroxyapatite and elastomer, and we treated with BMP2. If we couldn't get it to work with BMP2 treatment, then there's no point in going further. And there's the scaffold, and we got bone encapsulating it, quite vigorous growth of bone, so we thought we're viable. Now let's try to do the same thing while incorporating into the scaffold demineralized bone matrix particles. And this has some endogenous factors that might help the growth. And this is an unimplanted scaffold with hydroxyapatite. This is 2BM micro-CT, and this is a particle of DBM. So hydroxyapatite, elastomer around that, and DBM. Now, when we implant this, we get a vigorous response. One of the first things we look for is blood vessel infiltration into the large pores of the scaffold. And this is a 3D rendering. This is in color of the blood vessels. They were filled with contrast medium, and then we see them growing out of the existing bone and the presence of the synthetic hydroxyapatite containing scaffold around this. So we're making blood vessels go into all of the big pores within our scaffold, every single one. And that is the first thing you need for vigorous bone growth. This is just a different rendering. And then now if we look at an implanted scaffold, so here are some struts within the 3D design. This is 8 weeks after implantation. And let's blow up this area of the micro-CT picture into this slide. So what do you see in this picture? You see the particles, right, that are white. You see gaps among the particles. And what else do you see? What about these little squiggly things? It turns out that those are what we would call spicules. They tend to follow the boundaries of the DBM particles, and they have contrast that's identical with bone. So the contrast here in this pre-existing bone and the spicules within here is identical. That suggests they're bone. So we call them bone-like spicules because referees objected. So we wanted to identify whether this de novo bone formation within the DBM was something that in fact was bone. Here, just to show you that the contrast is identical, we take this area and compare to position 5. And here's a histogram of bone and spicules. There's the mean value in 0 to 255 scale for the spicule area 1 and 2 is 150. Bone on the other slide was about 144, so the spicules indeed have the same contrast as bone and suggests that in fact it is bone. That's not enough though. There are other things that are involved with bone. So we did fluorescence mapping at 2IDE, and this is the entire scaffold. This is the calcium map and the zinc map. And then if we zoom in here, we see there's calcium, zinc, phosphorus, and this is actually a spicule. We found the same spicule in diffraction maps, and it diffracts hydroxyapatite. Remember, the signature of bone is having calcium and phosphorus, okay, that's the part of the bone, in the same position as strong zinc signal. So with the diffraction data, with the fluorescence data, and the micro-CT data, I think we have bone. There's one other thing that we need to do to nail down that it is bone, and that is to have the D period present in the SAC signal. We haven't done that yet. Now, while talking about scaffolds and the spine, I wanted to change directions a little bit and talk about a slightly different application of position-resolved diffraction. And that is, here we have a vertebral body here, and something we're doing in situ loading at sector 1, and this is just a picture of that. And what we want to do is diffraction tomography. So we take the beam through the sample, collect the diffraction patterns, rotate through 0 to 180. So we have a bunch of different views. We have to translate to cover the entire slice. And then we can do integration of our rings in the horizontal sectors or the vertical sectors. So we can take the intensity here and here versus here and perform different tomographic reconstructions. And for determining deviatoric strain as a function of position under load, we compare the peak positions, the vertical versus the horizontal direction. So this is an unloaded sample early on, and this is the vertical azimuths reconstruction and the horizontal azimuths reconstruction, and they're identical. That's good. That means we're not getting some skewing effect from sampling different crystallites. We then make use of the fact that the radii changes along the vertical and horizontal direction because the load is deforming the unit cells. So we do Bragg's law, and we can work out what then the deviatoric strain is. These are just different reflections, and here are the deviatoric strains for one load state, the maximum load we took this to. The purpose is not to go into the details of this analysis. The purpose is just to mention that we can use diffraction information, tomographic reconstruction, in situ loading, and strain determination at the same time. I'm happy to talk to you more about that later on. Can we measure differences in bone quality in spine fusion model? You know, it's something very important to the physicians. So what we did was diffraction tomography of a piece of bone with a scaffold. There's a scaffold and bone. And the important thing in this example to note is that this is the diffraction pattern of bone. This is the diffraction pattern of synthetic hydroxyapatite. The things that I'm circling are the same diffraction peaks. So we're less resolved in bone, and we have sharp peaks. Let's suppose we do our diffraction tomography and do reconstructions with this peak position between the peaks in the synthetic hydroxyapatite and on one of the peaks of synthetic hydroxyapatite. What we do is then, between the synthetic hydroxyapatite peaks, here we can see the spine. And if we go on the synthetic hydroxyapatite peak, we now see the scaffold, which was invisible here. And that's because there is no diffracted intensity from the scaffold at this first angle. There is at the second angle. So we can, in principle, find bone within the scaffold and examine the diffraction signal from that, separate from the actual scaffold itself. So for me, that was very exciting. Now, in the last example, is of human enamel, which is actually a very fascinating material. In mature enamel, that's type O, has dense hydroxyapatite, 95–97% dense. It consists of a rod microstructure. Each of these rods is 5 to 10 microns wide and very long. Nanostructure of the rods are an array of very small parallel crystallites. The mean crystallographic orientation rotates from the center of the rod to the edge of the rod. So we'll have one orientation here, we move across there, and we'll rotate. Similarly, there's the crystallites, when observed with microscopy, are less ordered here, more ordered here. What we want to understand is the actual details of the crystallographic population. Diffraction peak widths are consistent with coherent domain sizes that are greater than microscopy's 10 to 20 nanometers. Not sure why we have this difference, but that's something we want to examine. Does the local crystallographic range of orientations vary? How does it vary, and how do lattice parameters vary across the rod? So in this schematic, we have the interrod region, the more disordered region there, the center of the rod here. What we want to differentiate and learn about is whether the crystallites have the same orientation here that rotates to the interrod region, or whether there's a range of orientations here and a range of orientations here. Once again, we've rotated from an average vertical to 30 degrees here, which would be the same as there and there. It's just that now we have a distribution. And this can be very important in terms of resistance to things like corrosion. So FIB was used to form a 1 micron thick samples, transmission X-ray diffraction, sampling of the crystallites on the following slide. So this is our schematic of how the sample is mounted, and then the area detector. This is our sampled volume, the little red area, so we might have different crystallite orientations there. This is the width, and this just shows that the crystallites may not be running along the sampling volume. So we end up sampling 2 times 10 to the 4 to maybe 1.6 times 10 to the 5 crystallites within this 0.4 micron by 0.4 micron by 1 micron thick sampling volume. So what happens then is not all of these crystallites are oriented for diffraction, and we see a bunch of small diffraction spots along each of the rings. So if we look at the quadruplet of reflections, we see these many small groups of diffraction spots along the different ones. And if we look at the azimuthal variation of intensity, this is the 022 reflection, the azimuthal variation of the 030, and the 112 and 121. Can we distinguish ordered from disordered volumes? And so what we're going to do is look at the azimuthal clustering of this quadruplet, here, this quadruplet of diffraction spots. So in a model, if there's no clustering, we get a coefficient, autocorrelation coefficient of 0.01. If we have a wide bump, it's 0.96, sharp bump, 0.87, et cetera, et cetera. So we can differentiate by this autocorrelation value the different clusterings that occur azimuthally around the diffraction rings. So here's real data from an ordered part of the enamel sample and the disordered part of the enamel sample. Here are the two things we're analyzing, the 030 and the 121 reflection for the two. Here are the azimuthal profiles of intensity. And if we compute the autocorrelation value, it's 0.78 for the ordered and 0.35. So we can then plot the autocorrelation value for each position across the map. And this is what we get on the left-hand side. So the darker values are poorly correlated, the lighter values are more highly oriented, and we see basically that's the type of structure we would expect. It exactly matches the orientation we would expect from how we milled the sample out of the things. We can partition, therefore, into two volumes, and we can look at this part of the sample and then look at what the lattice parameters are there, and look at the inter-rod regions, the more disordered regions, and look for differences of lattice parameter there. At this point, I'm not confident enough about what we've done to say that, yes, the lattice parameter is such and so here and such and so here. I am confident enough to say we see differences of lattice parameter in these two locations. So lattice parameter differs here to here. This is work that's underway and hopefully will be out for review in a month or two. So now, summing up, where I'm not really sure what I was going to say because I wasn't sure what I was going to say. It never comes out quite the way you plan it. Looking at various different things from an Egyptian mummy, which might be not just a cultural heritage object, but might be a surrogate for actually doing diffraction on a cadaver or on a living patient, perhaps. It's possible, for example, to take some of these techniques into a study that just received some publicity here of mapping cracking within skull bones from shock loading, that the Army is very interested in developing a new generation of helmets. Archaeological metacarpal bones, can we learn things about population lifestyle and health from bones from olden times? Continuing to work on that. So far we haven't had success, but you never know, keep trying. Developmental stages. What is going on in the growth bands? If we can understand the growth bands within teeth, we can think then about the actual growth processes that were going on and our interpretation of those growth processes. 3D scaffolds, I think we all don't want to have a spine fusion operation, but if we need one, we would like it to not fail 15% of the time. So hopefully this new generation of materials will help us improve the results of those kind of surgeries once it reaches human population. And there are other defects that need to be fixed as well in long bones and elsewhere. And finally, the human enamel. We're looking at a different scale and trying to understand the nanoscale variation of enamel and how that might contribute to things like dental caries, chipping, and then ultimately repair of enamel. And with that, this is my last slide. And even in this audience, I realize not all of us are fluent in fast Fourier transforms. So what this says is thank you very much, and I'm happy to answer any questions. So all of these examples were examples of biomineralization. We're looking at the endpoint as opposed to samples undergoing biomineralization. I did not emphasize, for example, the edges of the teeth or the edges of cementum where there's actually large peaks in zinc. We have work underway where we will be looking at, in fact, developing enamel and looking at what actually is going on. And a good model for developing enamel is not humans, because once our enamel is formed, it's there, and nothing changes, but rather incisors of rodents like rats and beaver. So if you look at the end of an incisor, you have a mature enamel. You look down toward the root, then you see less mature. So by sampling, for example, along the length of the incisor, you can look at different stages of biomineralization.
Is there a clear chemical or physical definition that differentiates a mineral which is no longer, let's say, living versus part of the tooth or any part of the body which is still developing?
That is a very interesting philosophical question, because many people think of the mineral as being dead. It's just being dead. Once it's there, it's dead, it doesn't change. That's not true. It's actually changing in composition, or the plates are maybe growing slightly. The mineral levels can be increasing slightly as the tissue matures. And bone, for example, is replaced repeatedly during one's lifetime. You have what's called bone remodeling. So cells come in, they dig out the mineral. So the actual process of forming the very first hydroxyapatite is still largely unknown. We sort of know where and when, but we don't really know even all of the protein actors that are going and interacting with it. So I tend to think of it more as an inorganic process that's helped by a nucleating substrate and various chaperones. I'm not sure that that is true. One situation where it appears to be true is in these demineralized bone matrix particles. So this is actually a bone particle that's had all of the all of the calcium and calcium phosphate removed from it. So it's essentially the material in which the mineral forms. And when we put it in the vicinity of an active source of calcium and phosphate ions, these synthetic hydroxyapatite particles, we see these spicules form. And I think that would be a cell-free inorganic nucleation process. There is a lot of talk in mineralization of bone, where they're talking about vesicles and amorphous hydroxyapatite being injected into the space. I don't know very much about that, and I have a lot of questions about that.
Stuart, thank you for the talk. Is there a qualitative difference if you have a metal implant, a prosthesis, and the bone grow around that? Is that a qualitatively different kind of bone than naturally occurs?
No, the bone that grows, period, is just about like any other bone, as far as we can tell. What will happen with bone growing around a metal implant, to make it different, is the fact that bone responds to the strain of daily activity. So if you have bone which is not being loaded, like for instance in an astronaut in weightless environment, the body will remove bone. it will remodel the bone. The total amount of bone in an astronaut who's been up for 6 months has gone down. A similar thing happens around a rigid implant, like, say, a titanium rod. The bone will tend not, in some cases, to adhere to the implant after a time. It will rather get removed by the remodeling processes. So a lot of times, this kind of scaffold, with its porous, not terribly stiff, is designed to give bone a chance to get growing and then ideally to go away, so that you're left with wholly native bone there. So I don't know if that really answers your question or not.
So you had mentioned tooth decay or cavities. I think of these as calcium, and what actually is decay?
So what happens in the mouth is it's a dynamic system. There's constant dissolution and remineralization of the calcium phosphate, particularly in enamel. And what will happen is you will get leaching out of the mineral due to the acid from the bacteria that are present within the mouth. And then you will typically get remineralization over the top of this demineralized volume. That demineralized volume is the caries, the cavity. And one hopes to have a treatment where you just sort of scrape off the outside and get it to remineralize, because you can sort of do this inorganically in the mouth, but that sort of treatment is not really very far along at all, as far as I can tell. Is there more to that? Yeah, if you get a good seal, you basically stop the progression of the dissolution. And typically what happens is that layer on the outside is somewhat porous. So you can get ion exchange in there. So what you do is you go ahead and seal it. And it could be with a polymer, or it used to be amalgam. I don't think they're using dental amalgam anymore.
So as a person that's used a lot of techniques and looked at a lot of systems, we got a spot. When the APSU comes online, is there one experiment that you'd like to do now that you can't quite do? You can just pick one and burn and do?
Well, there are actually so many things I'd like to do. It's the problem with my collaborators have is I keep doing new things, and it gets in the way of writing up the old things, and they're not so fond of that. They'd like to see the papers get out. I would probably use the brilliance to do things like the diffraction tomography, for example, that we're doing now. We're lucky if we can get a single slice in 2 or 3 hours with 25 microns of resolution. I'd like to be able to look at the same size sample, say a millimeter, a quarter of a millimeter, with 1 micron voxels in the same period of time. So really increased brilliance, and possibly playing games with other things to get more of a volumetric diffraction tomographic view. That said, all of the imaging things can really be helped by this, particularly if you have a coherent source and you're doing regular projection tomography. I think you could really do some very interesting things. And I haven't really thought about what you could do, but I think every time something like that's happened, we find out that there's one thing we knew we could do, and then there's like 4 or 5 other things we didn't even think about. Somebody notices something, and all of a sudden there's a new modality out there that everybody's trying to do. So I don't know. That's my take. It's a ways down the road. I can't think that far ahead. That's actually not true, but anyway.
All right, let's thank Steve.
Yeah, thank you very much again.